All right, everybody. Thank you very much for joining us this morning for this webinar. I am very excited and honored to be presenting in conjunction with Millrock Technology. And my name is Bowman Bagley, representing Advanced BioMatrix. And the title of this webinar is very long and potentially boring sounding, but Photocrosslinkable Extracellular Matrices for recreating an in vivo environment. But as I was trying to think about what I really wanted to talk about, this is the title and essentially the statement that kept coming back to my mind as, really this is our goal with these materials. And so I'm excited to talk about them today. If you have any questions, put them in the chat. And then at the end of the presentation, I'll open up the chat and I'll go through those one at a time and do my best to address those and answer those. And at the very end of the presentation, I have all my contact information, so you can reach out with additional questions, or if you want to request additional information. So that's me, Bowman Bagley with Advanced BioMatrix. My background is I studied neuroscience and business, and really with the intention of wanting to help understand the research, the science, help create new materials, and then also focus on how do we actually translate those from the lab into the hands of additional researchers to really progress science even faster. I think a lot of materials get created and then get stuck. And so I think it's for me, it's a lot of fun getting it out of the lab and into more hands so it can be a more functional and used material. I've been with Advanced BioMatrix for 8 years now, and been having a lot of fun. I don't want to do a huge plug into the company, but I think telling a little bit about where the company started and where it's going ties a lot into why we bring these types of materials and why our customers, we're seeing a huge spike in customers using these types of modified materials and maybe the reasoning behind that. So the very first product that we started with was a pure type 1 collagen called PureCol. It's 3 mg per mil enzyme extracted ATIVO collagen. And we, over the years, we started getting more requests of, can you have a higher concentration? Can we have an acid extracted telo collagen instead of an enzyme extracted ATIVO collagen? And so we built out our collagen portfolio, different species, powders and solutions, really addressing that market. But then over the years, we also started getting requests of, hey, our plastic dishes are too rigid. Can you have some soft substrates? And we created the Cytosoft line. We got requests for, hey, collagen typically is really, really soft hydrogels, it's cineresses. Can you create something that can be bioprinted with an extrusion printer? So we created these bioinks. And we got requests for different types of ECMs, fibronectin, vitronectin. And then, more recently, a big focus on modified proteins and sugars. And really, with each new product, our goal has been, how can we help the researcher get one step closer to really recreating an in vivo-like environment in your research? Now, I hate history slides because everybody on this presentation, this webinar, I'm sure knows a lot more about the history of science than I do. So I really simplified it to just kind of show, back in the day, it was focusing on, okay, we got to just study these cells. And then we realized, okay, media can really change how these cells, differentiate or grow. And then, we started looking at, okay, maybe 2-dimensionality is not as relevant as 3-dimensionality. And then from there, this is what I want to talk about. We're now really strongly focusing on, well, let's make sure that we have both the right protein or sugar, the right environment, and then also the right stiffness of that surrounding material. That hydrogel, that tissue needs to have the same stiffness and really represent the native environment. So now we're kind of in this phase focusing on 4 and 5. So the first question, and I'll get back to that in a second, but focusing on the extracellular matrix, these proteins and sugars, they're critical for cellular adhesion, communication, migration, differentiation, countless other functions. And the most abundant protein in the body, as you all know, is collagen. The most abundant glucosaminoGlycan is hyaluronic acid. And so those are, I put those at the top because they're kind of the two most prominent and most widely used. Laminins right there, fibronectin, and there's all sorts of other receptor proteins and cells and growth factors. Our body is composed of so many beautiful proteins and sugars and everything seamlessly working together. And so when we're talking to customers and researchers, the very first question we ask them when we're trying to help them advance their research is, what are the key ECMs in the environment or the tissue that you're trying to create? If they want to make a skin model, or they're trying to bioprint a piece of heart tissue or a liver or lung models, what are the ECMs of that environment? So let's first solve that problem, answer that question. And then once we understand the ECMs, we ask the second question: what is the stiffness of that environment that you're recreating? Years ago, I had made this graphic on the left with my wife. She did some graphic design work for us, and we looked at some publications and pieced this together. But I ended up finding a publication, the picture on the right, which is looks a little more, it's more scientific, but it really shows this broad range of tissues and the stiffnesses. If you're studying the brain, and you're going to be in a very, very soft environment, whereas bone is going to be significantly just kind of off the chart, way stronger, and then everything in between. So a lot of researchers will have the perfect cells, the right media. It'll be a 3D environment. They'll have the right proteins, but then they're growing neurons in an environment that's as strong as cornea or bone or tendon. And so stiffness can affect almost as much as the protein, right? It can propagation, differentiation. I guess the list is right there at the bottom, but gene expression, morphology. There's been hundreds or thousands of publications now showing how subtle changes in the stiffness of that environment can drastically change the viability or health or just even morphology of your cells. And so we're focusing on, okay, how do we tailor both the extracellular matrix environment and then the actual kind of macro stiffness of that environment? And so from those, so initially the first answer that we had was, okay, our collagen materials. So this is a graph where we're looking at the gelation of, or 3D gelation of our collagen hydrogels at 37 Celsius over time. And then you're looking at the strength of the gels. You'll see the telocollagen gels are the ones that gel very quickly and form stronger gels. The atelocollagens gel much slower and much softer. And this was great for a little bit, but you can see that the kind of the upper range of these unmodified collagens is really about 10,000 pascals. There's methods to super concentrate the collagen, but it's much more expensive and difficult, and maintaining sterility and all that. So this was good a little bit, and there's some tunability, but it didn't really address the full range that was needed to recreate heart, muscle, tendon, cartilage, cornea, bone. So that led us into the creation of these methacrylated extracellular matrices. And so the ones that we started on, I think, are the ones that we try that really help recreate the human body, right? We started with collagen, gelatin, and hyaluronic acid. And collagen being the most abundant protein, hyaluronic acid being the most abundant glucosaminoGlycan, it kind of covers the most of the body. So we have photocol, photogel, photo-HA, photodextran, and photoalginate. You'll also see that with the gelatin, there's 2 different degrees of methacrylation, 95% high and 50%, say, kind of medium. With the methacrylated hyaluronic acid, we run two different reactions, which results in a stiffer and a softer hydrogel. And really the goal is to allow tunability, right? Methacrylation, what it does is methacrylation allows these materials to be photocross-linked. And so you can now photocross-link these materials and have a huge range of stiffnesses, soft to really stiff. And they're being widely used for extrusion printing, inkjet, DLP printing, molds, basic 3D hydrogels, tissue models, all sorts of things. So it's a lot of fun. Now, let's talk about the tunability and how these materials are so tunable. The first one I'll talk about is the concentration of the protein or sugar. So I'm not supposed to plug Millrock, but we just bought one of their lyophilizers because we lyophilize all these products, all the methacrylated ones. And we just bought their massive 7-tray. They'll probably say it's small because they have even bigger ones, but we bought their 7-tray lyophilizer. We ran a LinkedIn poll to get some feedback on what we should name it, because we have a couple other lyophilizers and we need to keep them separate. So that one we've called The Rock, because it's big and strong, and it's a little play off of Millrock. So I'll post a picture soon of the big rock's face that we have on our lyophilizer. But we lyophilize all these materials to give you this tunability. So the gelatin, for example, the photogel, you can concentrate that from 1% to I wouldn't go much higher than 20%, but you can go higher. 1% to 30%, we'll say. You get this huge range of concentrations. We can look at the degree methacrylation. So the Gelma has the two different, high and medium methacrylation. How does that affect the stiffness of the environment? There's a bunch of different photoinitiators. I think the three most popular right now are LAP, Ergocure, and ruthenium. Doing different photoinitiators, different concentrations of those photoinitiators. On our website, we typically recommend the lowest range of photoinitiator to be on the safe side. But we've seen, with LAP, for example, we've seen researchers using 10 or 50 times higher concentrations of LAP. And then it also depends on if you're using cells or not. You can get away with higher concentrations and avoid toxicity, cytotoxicity. We can you can tune the photocross linking time, how long you cross link it for, what's the temperature of the protein when you cross link it, the intensity of those lights. You can mix and match different ECMs. We start thinking about, I want to recreate a native environment. I should probably have some collagen and some hyaluronic acid. I want to mix these two components together. And the list of the methacrylated ECMs we have, that's going to continue to grow this next year. We're putting a strong focus on it because the materials are so versatile and there's so many fun knobs to turn. So we're having a lot of fun with it. So really, by adjusting these various knobs, researchers can create a 3D hydrogel with the essentially correct ECMs in the physiologically relevant range of stiffness. So I'm going to show some very basic case studies. All of the data, how we ran these tests, the parameters, the machines we used, all of that is found on our website on the white papers that are tied to these studies. And you can also reach out to me. I'll just send them to you directly if you want. And keep in mind with rheology, my rheology results are going to be different than your rheology results, which is kind of funny to say in science. But rheology is so dependent on testing methodology. Are you using a machine that uses vibrations or lasers? Are you pulling the sample? Are you straining, twisting, compressing, stretching? All these different methodologies, as well as just user handleability, temperature, humidity of your room. All these things play an effect. So I want you to focus on really, generally the values, but then also relative values between the different concentrations within this one, or these values compared to the next study I show. This particular test was performed at 25 Celsius. So let's dive into this. So we took the methacrylated gelatin, the 95% methacrylated. we allowed it to equilibrate for 5 minutes, and then we cross-linked it for 10 minutes, and then we let it sit for 5 more minutes. And that's the data that we're looking at. This particular one is used with LAP and 405 nanometer blue light. And again, all the data is on the white paper. So you see that by changing the concentration from 5% to 10%, you're increasing the stiffness from about 5,000 to close to 40,000 pascals. And then again, from 10% to 20%, you're going from 40,000 to, we'll say 120 to 140,000. So you get this one protein, this methacrylated gelatin, can almost by itself be tuned to cover essentially almost the entire physiologically relevant range of stiffness that you might need for a product, which is really cool. The second one, now we said, okay, well, that's the 95%. Let's take a look at the 50%. It's half as methacrylated, and in a kind of a beautiful science, the stiffness values are essentially half as well. So the 20% gelatin cross-linked the exact same way, but with the 50% methacrylation had a stiffness of essentially half of the 95% methacrylation at 70,000 and about 15 to 20,000 and then 2-ish thousand at the bottom. So just by adjusting the methacrylation, you can have a huge play on tunability. And now the question I know someone's going to ask is, well, if you're changing the concentration, you are also changing the porosity. How does the porosity affect the cells? That's a great question. And we haven't measured porosity yet or really dove into that. We're just strictly looking at stiffness at this point. But we recognize that the concentration will change the porosity, and that will induce some additional questions, of course. The third thing we wanted to look at is temperature. So, the reason we did this study is that we had a customer call and say, I followed your protocol and I made a gel, but it just, I cross-linked it and it was way softer of a gel than I thought it would be. And we said, okay, well, tell me walk us through what you did. And they warmed it up to 37, they kept it at 37, and then they cross-linked it. And we said, we've never looked at cross-linking, the resulting stiffness at 37 versus 25 or 20 room temperature. So we just quickly went back to the lab, ran some tests, and got some really fun data where simply by cross-linking the gelatin at the higher concentration, the higher temperature, they got a significantly softer gel. Whereas at the lower temperature, you get a much stronger gel. And with the gelation kinetics of gelatin, it makes sense. And so the results made sense. We just had never thought of it before. And so we're extremely grateful for researchers just asking us these questions, because it gives us an excuse to go play in the lab, run some studies, and get some of this data. And every time we do one of these studies, we post it on our website. We'll share it on LinkedIn. We want to share as much data and information as we can, because I see a tremendous value in sharing data, so that all the mistakes that I've made in the past, you don't have to make those same mistakes, and everything that we've learned, you can learn as well, and hopefully start at a level higher than where we started. I think it's important for science to continue to build off each other. So if you have particular rheology requests or questions like that, we'd love to work and try to just answer some more of these questions together. So that was kind of 3 quick case studies. Our future studies, again, we're diving further into ECM concentration for more of our products. We're looking at more, a broader range of methacrylation, really just trying to have more tunable materials for researchers. We're going to do some more studies comparing photoinitiator, which one is the most efficient, LAP, Ergocure, ruthenium, VAO86. The photoinitiator concentration, what's the limits of that? How high can you go? Again, more cross-linking time, how long can you zap it and before you either fry your cells or it just runs out of cross-linking sites. And then, we really want to start playing around with more of mixing and matching these ECMs. Again, being able to combine if you want to recreate a native environment, you start thinking about the collagen and the hyaluronic acid really interacting together. So, 1, 2, 3, 4, 5, we've kind of addressed, and we're really actively addressing 4 and 5 right now, the ECM and the stiffness. The next step really, in my mind, is the geometry, right? We're looking at, creating aligned fibers for cells to kind of travel along or align along these aligned materials, or cellular alignment and cellular deposition, or multicellular, highly organized geometries of the cells. And when you start combining cells and media and the three-dimensionality and the right proteins and the right stiffness in the right shape, we're just that much closer to having the most physiologically relevant, human tissue models for, drug delivery, drug studies or toxicology studies. And we're just getting that much closer and advancing our science just that much more. And a lot of this geometry is going to be done with 3D printing. I'm not going to pretend like I'm an expert at the actual equipment, but there's 2-photon and lasers and DLP, extrusion, inkjet, holographic. There's even a new printer that uses sound vibrations. So I'm not going to dive into the printers, but there's so many options out there, and these methacrylated, modified materials are really a key component towards really recreating an in vivo environment in our research. So that's me again. The QR code takes you to the website, so you can see some of our materials. You can also go to the Contact Us tab on the website. There's my personal email. You can email me anything you want. Not spam, but I love to collaborate, ask me questions, work together if you want some studies done. Or another great way is to reach out to me on LinkedIn. I'm on there every day, and happy to connect through there.